Okay, since we understood about the small o notation, now let's go and understand about the small omega notation. So same like how we have learned a multiple definitions for small o notation, here also I will give you the multiple definition of the small omega as well, right? And the small omega will be represented using the Greek letter as this. This is the small omega notation. Now let me give you the first definition of the small omega. So as per this definition, we can say that my f of n is equal to small omega of g of n, small omega of g of n, if and only if g of n is equal to small o of f of n, right? So this is one of the best and most intuitive definitions of the small omega. Essentially, it says that my f of n grows strictly faster than the g of n function, right? In other words, g of n is the small o of f of n. So this is the one of the best and most intuitive definitions of the small omega. Even you can take an example. Earlier we took an example, right? So 2n, which is equal to small o of n square, in terms of small o, 2n is equal to small o of n square. What does this imply means? It implies that n square is equal to small omega of 2n, or you can write it down as n, since the constant factor do not matter asymptotically. This is the same as n square is equal to small omega of n. This is a very interesting and useful way of understanding of small omega. Now the second example or the second definition of a small omega is as follows, right? So we can say that my f of n is equal to small omega of g of n. So this is more a mathematical definition of a small omega. So my f of n is equal to small omega of g of n if and only if for all c, constant c is greater than 0, there exist, so I'm using this symbol to represent that there exist n0 should be greater than 0, such that my c into g of n is greater than or equal to 0, that means 0 less than or equal to c into g of n, which is strictly less than f of n for all value of n is greater than or equal to n0. So this is the mathematical definition of the small omega here. Again, you can notice the difference between the big omega and the small omega. Same like how we discussed about the big O and the small O. Here we can also easily differentiate you can find the difference between the big omega and the small omega. So in case of big omega, what we can say, there exists some constant. So some constant c should be greater than 0 and some n0 value that should be greater than 0, such that my c into g of n is less than or equal to f of n for all n greater than or equal to n0. So the term you should remember here is some constant c here. But in case of small omega, we can say that for all constants, for all values of c should be greater than 0 and it exists n0 should be greater than 0, then we can say that c into g of n strictly less than f of n for all n is greater than or equal to n0. So this is the definition of the small omega. So the major difference between both of them here is the terms. For all c versus there exists some c here. So this is the key difference between the big omega and the small omega. So this is the main difference between both of them. Similarly, how we have solved it for small o, you can also take an example to prove this statement, right? So you can take an example as n square by 2, which is equal to small omega of n, right? Same like that, you can also prove that n square by 2, which is not equal to small omega of n square. So, right? So I would recommend you to please solve these two statements, same like how we have proved it for the small o. right? Now let's go and understand the third definition. This is more calculus way of defining the small omega. So the third definition says that we can say that my f of n is equal to small omega of g of n if and only if limit n tends to infinity, my f of n by g of n, which is equal to infinity. So this definition is very similar to the alternative definition we saw for small o. Again, let's take an example to prove this statement. Understand this statement much better, right? Let's say my f of n is equal to n squared by 2. And let's say my g of n is equal to n, right? Now I want to prove this statement. So now limit n tends to infinity, n square by 2 by n square, by n. So in this case, what will happen here? So which is equal to limit n tends to infinity, n by 2. So therefore, n square by 2 is small omega of n, right? So as the value of n goes to infinity, this value will be almost equal to infinity. So I would say that my n square by 2, which is equal to small omega of n here. So this condition holds, or this statement holds true. Now consider the other case, another example. This is my example 1. Let me give you another example. Let's say my f of n is equal to n square by 2 and g of n is equal to n square. So what will happen in this case? Limit n tends to infinity, n square by 2 by n square. So n square will get cancelled. So what is the value you are going to get? Limit n tends to infinity, we have 1 by 2, which is equal to some constant 1 by 2, which is not equal to infinity. So from this we can say that n square by 2 is not equal to small omega of n square, hence proved, right? So this limit based definition is very often very easy to apply and understand it, right? Now the big question I have here is important, possibly confusing question here is, we have learned about big O notation, big theta notation, and big omega notation, and small o notation, and the small omega notation. So there are 5 notations in total. Now the question here is, how are they related to each other? How are they related to each other? So this is the very interesting question I have, right? This is the one big question. Another question here is, let's say I have some functions like n, n square, n cube, or 2 power n, or log n, right? N log n, right? How are these functions are related? How do we compare each of them? What is their order of growth? So what is their order of growth? Order of growth. So there is a concept called order of functions, and there are relationship between all these asymptotic notations which we have learned so far. So in the next discussions or the next videos, we will learn about the relationship between these 5 notations, and also we'll understand the order of these common functions what we have, hierarchy or the order of common function, and also we'll understand about how all of these is applied in the real world algorithm analysis. So right now I just gave the definitions of what is big O, what is big theta, and what is big omega, small o and small omega, right? So we will go through many examples and solve some several problems. Once you see these concepts applied repeatedly, they will become much clearer and much more intuitive. So in the next upcoming videos, we'll understand how they are related to each other. So that is the one of the big question we will able to understand.